The National Electrical Code, or NEC, requires that all power to a building be disconnected when the main disconnect is opened. In this situation, the feed to the 75 kVA transformer is not controlled by the building's main disconnect, which is a code violation. It is advisable and necessary to reconfigure the electrical system to ensure that all power to the building can be disconnected by the main disconnect. This will improve safety and compliance with the NEC. A proposed solution seems viable. The steps are: firstly, install a new fuse disconnect in the load side of the building's 400 amp disconnect. Secondly, size the fuse disconnect and wire appropriately for the 75 kVA transformer. Thirdly, move the 75 kVA transformer inside the building electrical vault. Fourthly, connect the 75 kVA transformer to the new fuse disconnect. Fifthly, feed the 240 volts loads from the 75 kVA transformer. Sixthly, move the power panel for the 240 volts loads to a more accessible location. It is important to coordinate with a qualified electrician to ensure proper installation and compliance with all applicable codes. Consider upgrading the 75 kVA transformer to a 3-phase transformer if the 240 volts loads increase in the future. Ensure that all conduits containing circuits from both the 75 kVA transformer and a building's main system are properly labeled and separated to prevent accidental cross-connections. Update the building prints to reflect the new electrical configuration. Let's delve a bit deeper into the considerations for this type of electrical modification. The primary goal is to ensure compliance with the NEC, enhance safety, and create a more manageable and understandable electrical system. Starting with the disconnect, the selection of the new fuse disconnect on the load side of the existing 400 amp disconnect is crucial. This disconnect acts as a secondary overcurrent protection device specifically for the 75 kVA transformer. The size of this disconnect must be carefully calculated based on the primary current of the 75 kVA transformer. The formula to determine the primary current is kVA times 1000 divided by the primary voltage. In this case, 75 kVA times 1000 divided by 480 volts. This will give you the full load amps on the primary side. Once the primary current is calculated, select a fuse and disconnect rating that is appropriate for that current. NEC Table 450. 3. It dictates the overcurrent protection requirements for transformers. Generally, the overcurrent protection should not exceed 125% of the transformer's rated primary current if using a circuit breaker, or 125% if using fuses rated 600 volts or less. The wire size connecting the 400 amp disconnect to the new fuse disconnect and then to the 75 kVA transformer must be sized according to the ampacity requirements of the NEC. Use NEC Table 310. 16 to determine the appropriate wire size based on the calculated primary current of the transformer, taking into account the insulation type and the ambient temperature. Remember to consider voltage drop. A voltage drop of more than 3% in the branch circuit or 5% on the feeder can cause inefficient operation and premature failure of equipment. Use a voltage drop calculator to ensure that the wire size is adequate for the length of the run. Moving the 75 kVA transformer inside the building electrical vault is essential for several reasons including safety, accessibility, and environmental control. Electrical vaults are designed to contain electrical equipment and minimize the risk of fire or electrical hazards. Before moving the transformer, ensure that the vault has adequate ventilation and is free from any obstructions. The transformer must be installed according to the manufacturer's instructions and all applicable codes. This includes proper grounding and bonding. When connecting the 75 kVA transformer to the new fuse disconnect, use appropriately sized conductors and connectors. Make sure all connections are tight and secure. Use a torque wrench to tighten connections to the manufacturer's specifications. Grounding and bonding are critical for safety and to prevent electrical shock hazards. The transformer must be properly grounded to the building's grounding electrode system. Use a grounding electrode conductor of the appropriate size, as specified in the NEC. Bond all metallic parts of the transformer enclosure and the disconnect to the grounding system. Feeding the 240 volts loads from the 75 kVA transformer involves careful circuit planning. Determine the total load in amps of all the 240 volts circuits that will be fed from the transformer. This will help you select the appropriate size conductors and overcurrent protection devices for the secondary side of the transformer. The secondary voltage of the transformer is 240 volts single phase. Therefore, the secondary current can be calculated as kVA times 1000 divided by the voltage. In this case, 75 kVA times 1000 divided by 240 volts. This will give you the full load amps on the secondary side. Install a new distribution panel or subpanel to feed the 240 volts loads. The panel should be sized appropriately for the total load and should have enough spaces for all the required circuit breakers. Use appropriately sized circuit breakers to protect each 240 volt circuit. The circuit breakers should be sized according to the ampacity of the conductors and the requirements of the NEC. Moving the power panel for the 240 volts loads to a more accessible location is important for maintenance and troubleshooting. Choose a location that is well lit, easily accessible, and free from obstructions. The panel should be mounted securely to the wall or other support structure. Label all circuits clearly and accurately. This will make it easier to identify and troubleshoot problems in the future. After completing the electrical work, it is essential to inspect and test the system to ensure that it is safe and functioning properly. Use a multimeter to verify that the voltage and current levels are within acceptable limits. Use an insulation resistance tester to check the insulation of the conductors. Perform a ground impedance test to verify that the grounding system is effective. Document all changes to the electrical system. Update the building prints to reflect the new electrical configuration. This will make it easier to maintain and troubleshoot the system in the future. Keep a record of all inspections, tests, and maintenance performed on the electrical system. This will help you track the performance of the system and identify potential problems before they become serious. By following these steps, it is possible to correct the electrical code violation, improve safety, and create a more manageable and understandable electrical system. Remember to always consult with a qualified electrician to ensure that all work is performed in accordance with all applicable codes and regulations. In addition to the steps outlined above, there are several other considerations that should be taken into account when reconfiguring the electrical system. One important consideration is the potential for future expansion. If there is a possibility that the 240 volts loads will increase in the future, it may be wise to upgrade the 75 kVA transformer to a larger size. This will provide additional capacity and prevent the need for costly upgrades in the future. Another consideration is the efficiency of the electrical system. Transformers are not 100% efficient. They consume a small amount of power in the form of core losses and copper losses. The efficiency of a transformer is typically between 95% and 99%. When selecting a transformer, choose one that is energy efficient. This will save money on energy bills and reduce the environmental impact of the electrical system. The location of the transformer is also an important consideration. The transformer should be located in a well-ventilated area to prevent overheating. It should also be protected from moisture and other environmental hazards. If the transformer is located outdoors, it should be enclosed in a weatherproof enclosure. The type of transformer is another important consideration. There are two main types of transformers: dry-type transformers and liquid-filled transformers. Dry-type transformers are typically used indoors, while liquid-filled transformers are typically used outdoors. Dry-type transformers are generally more expensive than liquid-filled transformers, but they are also safer and more environmentally friendly. The installation of the transformer should be performed by a qualified electrician. The electrician should follow all applicable codes and regulations. The transformer should be properly grounded and bonded. The connection should be tight and secure. The wiring should be protected from damage. The maintenance of the transformer is also important. The transformer should be inspected regularly for signs of damage or wear. The connections should be checked to make sure they are tight. The wiring should be inspected for signs of damage. The transformer should be cleaned regularly to remove dust and dirt. By taking these additional considerations into account, it is possible to create a safe, efficient, and reliable electrical system. Remember to always consult with a qualified electrician to ensure that all work is performed in accordance with all applicable codes and regulations. Furthermore, let's elaborate on specific aspects of the installation, starting with the fuse disconnect selection. When choosing the fuse disconnect, it's not just about the ampacity. Consider the interrupting rating. The interrupting rating of the disconnect switch and fuses must be sufficient to interrupt the available fault current at the point of installation. This is often overlooked but critical for safety. An insufficient interrupting rating can lead to catastrophic failure during a short circuit. To determine the available fault current, you'll need to perform a fault current calculation. This calculation takes into account the utility's available fault current, the transformer impedance, and the conductor impedance. Electrical engineers typically perform these calculations. Once you have the available fault current, select a disconnect switch and fuses with an interrupting rating that is equal to or greater than the calculated fault current. Now let's talk about transformer placement. The NEC has specific requirements for the installation of transformers, especially within buildings. Section 450 covers these requirements in detail. Ensure that the transformer is readily accessible for inspection and maintenance. Maintain proper clearances around the transformer for ventilation and fire safety. If the transformer is located in a dedicated room or vault, ensure that the room meets the NEC requirements for transformer rooms, including fire resistance and ventilation. Regarding conductor selection, the NEC provides guidance on conductor ampacity, dating factors, and allowable voltage drop. Use the appropriate tables in Article 310 to determine the correct conductor size. Remember to apply dating factors for ambient temperature, the number of conductors in a raceway, and other conditions of use. Calculate the voltage drop to ensure that it does not exceed the NEC recommended limits. Excessive voltage drop can cause equipment malfunction and premature failure. On the topic of grounding and bonding are critical for safety and to prevent electrical shock hazards. The transformer must be properly grounded to the building's grounding electrode system. Use a grounding electrode conductor of the appropriate size, as specified in the NEC. Bond all metallic parts of the transformer enclosure and the disconnect to the grounding system. Ensure that all grounding and bonding connections are tight and secure. Use approved grounding and bonding connectors. When it comes to labeling, proper labeling is essential for safety and to facilitate future maintenance and troubleshooting. Label all disconnect switches, transformers, and panels with clear and concise descriptions. Use permanent labels that are resistant to fading and weathering. Update the building's electrical drawings to reflect the changes made to the electrical system. After the installation is complete, perform a thorough inspection and testing of the electrical system. Use a multimeter to verify the voltage and current levels. Use an insulation resistance tester to check the insulation of the conductors. Use a ground impedance tester to verify the integrity of the grounding system. Perform a functional test of all equipment connected to the electrical system. Now let's discuss potential upgrades. Consider upgrading the 75 kVA transformer to a 3-phase transformer if the 240 volts loads increase in the future. A 3-phase transformer can provide more power and is more efficient than a single-phase transformer. If you decide to upgrade to a 3-phase transformer, you will also need to upgrade the wiring and overcurrent protection devices. Also, consider installing a power quality meter to monitor the electrical system. A power quality meter can measure voltage, current, frequency, power factor, and other parameters. This information can be used to identify potential problems with the electrical system and to optimize its performance. Let's consider energy efficiency improvements. Replacing the existing transformer with a high-efficiency transformer can reduce energy consumption and lower operating costs. High-efficiency transformers are designed to minimize core losses and copper losses. These transformers can save a significant amount of energy over the life of the transformer. Consider installing energy-efficient lighting and equipment. Energy-efficient lighting and equipment can reduce energy consumption and lower operating costs. There are many different types of energy-efficient lighting and equipment available, so it is important to choose the right products for the application. Consider implementing a power management system. A power management system can automatically turn off lights and equipment when they are not in use. This can save a significant amount of energy, especially in buildings with a lot of unoccupied spaces. Consider performing a regular energy audit. An energy audit can identify areas where energy is being wasted. This information can be used to develop a plan to reduce energy consumption. Let's cover safety practices and procedures. Always de-energize electrical equipment before working on it. Use lockout-tagout procedures to prevent accidental re-energization. Wear appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools. Work in a well-lit area. Keep the work area clean and free of clutter. Be aware of the potential hazards of electricity. Follow all safety procedures and regulations. Let's discuss troubleshooting techniques. Use a multimeter to measure voltage, current, and resistance. Use a clamp-on ammeter to measure current without disconnecting the circuit. Use an insulation resistance tester to check the insulation of conductors. Use a ground impedance tester to verify the integrity of the grounding system. Use a circuit tracer to locate circuits. Use a thermal imager to identify hotspots. Consult with a qualified electrician if you are unable to troubleshoot the problem yourself. Now let's cover documentation. Maintain accurate and up-to-date electrical drawings. Keep records of all inspections, tests, and maintenance performed on the electrical system. Keep records of all electrical equipment and components. Keep records of all electrical accidents and incidents. Finally, let's discuss code compliance. The NEC is a comprehensive set of standards for electrical installations. It is important to be familiar with the NEC and to follow its requirements. The NEC is updated every 3 years, so it is important to stay up to date with the latest changes. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations. It is important to be familiar with these codes and regulations and to follow their requirements. The electrical system must be inspected by a qualified electrical inspector. The electrical inspector will verify that the electrical system meets all applicable codes and regulations. By following these guidelines, you can ensure that the electrical system is safe, efficient, and code compliant. Remember to always consult with a qualified electrician to ensure that all work is performed in accordance with all applicable codes and regulations.